1.4 Graphs of basic functions. A function is continuous over an interval if there are no missing values of the domain. In other words, it's continuous if you can trace the graph without lifting your pencil, all right? So when we talk about continuity or interval of continuity, we're basically talking about the domain, all right? So keep that in mind. We've talked about domain a lot, domain and range. Interval, continuous, we're talking about domain. So if you look at this graph in example 1, it says describe the intervals of continuity for each function and where the function is increasing, decreasing, or constant. Imagine if you were trying to trace this graph from left to right. If I traced it right here, and it's kind of hard to see, but there's a hole. If you were tracing, you'd have to pick up your pencil to jump over this hole and then put it back down here to trace. So this one is not continuous the whole time. It's not continuous. So describe the intervals of continuity. Well, if you think about it, this is continuous over, and then, the domain starts at negative infinity, and I traced until I got to 0. Remember, I'm looking at the x numbers. I'm not looking at the 2. I'm not looking at the y number. I'm looking at the x number. And when I got to the middle right here at x is 0, that's when I had to jump over that hole. So it's continuous over the interval from negative infinity to 0, parentheses, because we're not equal to that 0. Now we're going to union that with the other half, and that's where I put it down, just after the 0 and going over to positive infinity. So I would union that with 0 to positive infinity. Bless you. If you think about what this means, it means everywhere except 0. That's what that means. All right, you wouldn't use brackets around the 0 because that would say equals 0, and then that would be just everything. I'm trying to remove that 0. And so that's the interval of continuity right there. As far as increasing, decreasing, and constant, well, again, as you're tracing this part is increasing. So we would say it's increasing from negative infinity to 0. And then this part's where it's decreasing. It's going downhill. It's decreasing from, I'll move over here, 0 to positive infinity. So then the other one, a weird graph because it looks like a W, but I never had to pick up my pencil. It's continuous the whole time. Oh, and by the way, these arrows here indicate that it goes on forever. So I don't really care to draw this, but this thing goes on forever and ever and ever, right? That's what the arrows indicate. I think a few of you missed that point on a quiz, on the quiz that we just took. But if you think about where this is continuous, it's continuous over the whole thing, over the entire domain, or in this case, all real numbers, right? Continuous over negative infinity to positive infinity. It's continuous the whole time. Think about domain. If you squashed this onto the x, it's covering the entire x-axis. It's continuous the whole time. I never had to pick up my pencil. Where is it increasing? Well, it's increasing here and here, right? That's where it's increasing. So we look at the domain, and this is -2 to 0, and that's -2 to 0, and that's +2 to infinity. So it's increasing in 2 spots. Let's go green. It's increasing bracket -2. That's supposed to be a -2. To 0. And it's a bracket this time because you could actually equal those numbers. Unioned with bracket 2 to infinity parentheses. That's the part of the graph that's increasing. So then decreasing, you look at decreasing as this part and this part. So it's decreasing from negative infinity to negative 2, bracket, unioned with 0 to 2. Neither one of these is ever constant. So I know it's said in the directions or constant, but neither one of these is constant. Constant would be like flat. Now, parent functions, when we get to parent functions, I'm going to unzoom this so we can see all 6 of them. You need to memorize these basic shapes, okay? Memorize these basic shapes. You already know some of them. You knew x squared was a parabola shape. It's a U shape, but some of those others maybe you didn't know. You should have known an absolute value was a V shape, all right? But y equals x, y equals x is a very basic line, right? And y equals x specifically looks like this, but you understand that I could change that. We could say y equals 1/2 x minus 7. And that's just a child of the parent function. The parent function is like the most basic line that we can possibly draw. Okay, the most basic one of these that we can possibly draw. All right, and so of course with a parabola, I could make it a lot more complicated, and I could move it over and up or whatever, but that's a child of the parent. The parent is just the most basic. And so you need to have the parent functions memorized. What is the shape? Sometimes I call the x cubed function the disco function. If you can imagine, there's a famous movie where a guy like dances and he kind of, one of his dance moves looks something like this. And so I might call that the disco function or something like that. But you need to memorize those shapes. The square root function looks like this, and a cube root function is like a sideways disco. One other thing that you need to memorize, and I think this will come up in your homework assignment, is this parent function right here is called the identity function. Y equals x. It is itself. Y equals x. It is itself. It's its identity. So that's called the identity function. I don't really think that's a huge deal, but it's definitely going to come up on your homework at some point. But you think about the domains and the ranges of these functions, but you need to memorize those shapes. You need to know those shapes. If you saw an absolute value function in your homework, you should know that it's a V shape. Now we talk about piecewise. And for some reason, piecewise functions kind of blow people's minds. I want you to get out Desmos. I think Desmos will really help if we can graph what this thing looks like. Okay, so get out Desmos. If you need to go through Goldadder, do that. It's easier for me, so I don't have to type it. Okay. So that's not it. Where are we? Piecewise function. It's like a Frankenstein's monster kind of put different functions together into one function. All right, and people their eyes go crossed because it looks so complicated, but it's not really that bad. All right, we are going to start with this piece of the piecewise function, 2x plus 4. 2x plus 4. So I want you to enter the equation on Desmos, y equals 2x plus 4. And where can I type? Isn't there a keyboard somewhere? Over here, maybe. Alrighty. So y equals 2x plus 4 looks like that line, and that shouldn't be a big shock to you. all right? But we don't want the entire line. We want just a piece of it. And here's what's kind of weird, all right? And people will ignore this when they look at piecewise functions because it's hard, but we only want the piece of the function where x is less than 1. All right, so if you imagine squashing it onto the domain, we only want x is less than 1, and people have a hard time imagining that. So what I want you to do then is, okay, on the same line as the equation, hit a space, and then I want you to find the squiggle brackets. Squiggle brackets on my keyboard is over here next to the P. I'm going to have to hit Shift to get there. Shift, squiggle bracket. And then what was it? X is less than 1. I'm going to type X and less than 1. And I'm going to close my squiggle. All right, now check out what that did to my graph. What did that do to my graph? It only shows the piece of my graph where x is less than 1. Imagine if you found the domain of that piece. If you squashed that piece onto the x-axis, it's literally going to say x is less than 1. Okay? Now, one thing that's a little bit confusing is the end point. Since it says less than does not mean equals, and so it's like an open circle. So if I was drawing this by hand, I would want an open circle on the end. So let's go ahead and do that in Desmos. Okay, a point is going to be an xy. So let's do parentheses, and then we need to know those coordinates. Can you see on yours? Is it 2, 6? Is that what the point is right there at the end of it? I think it's 2, 6. It's 1? Yeah, you're right. My scale. Okay, I was counting tick marks. I wasn't looking at the scale. Okay, you're right. It's 1. Great. 1, 6. Okay, good. Puts a point there. Puts a point there. That's good, but I want it to be open. So what you can do, I don't know if I'll be able to do this, but long press on the blue dot over here. Nope, it didn't work. Settings gear. Nope, it didn't work either. Well, how can I do this? Well, there we go. Okay, I'm going to change it to an open circle like this. And I'm also going to make it red. And I'm also going to blow it up. Let's make it size 15. So it's an open circle. That open circle means we don't count that point right there. Okay? We don't count that point right there. Now, nope, all over the place here. I've just graphed this piece. But now I want to graph the other piece of the function. Okay? So now I'm going to graph y equals 4 minus x. So let's make a new equation and do y equals 4 minus x. And again, I've got too much. I don't want the entire equation. I just graphed the entire equation, y equals 4 minus x. I don't want the entire thing. I only want if x is greater than or equal 1. So again, I'm gonna do this thing of where I restrict the domain. That's what I call it. That's what it's called. We're gonna restrict the domain. So space and squiggle, and we want x is, I think I can just type greater equal 1. Close squiggle. All right, great. Notice we've got it. Notice it showed up there, right? There it is. We've got the other piece of the function, other piece of the piecewise function. But it says equals. X is greater than or equal 1. So this would have like a filled in dot, I suppose. So let's put a filled in dot over there. What are the coordinates of that point, by the way? 1, 3. Is that what it is? 1, 3. 1, 3. Close. And that's really pretty good. I could change the color to make it look nice, but that's the function, okay? That is the function, this piecewise function. And people have a really hard time understanding that we just want a piece of this one and a piece of this one. But that's all it is. Piecewise functions are not the end of the world, not the hardest thing in the world to do, but people really struggle with it. So when you're graphing the first piece, 2x plus 4, think about how you would graph the line. If you were back in algebra class, you'd go up 4, and you'd go up 2 and over 1, up 2 and over 1, up 2 and over 1, or down 2 and left 1, 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 and then shoot. Oops, where'd it go? I missed. Anyway, that's wrong because I didn't restrict the domain. I don't want that entire thing. I only want the piece of this that's less than 1. So I've got, I got to get rid of a lot of this, right? I got to get rid of, well, those are fine. And that one's fine. And, I wouldn't really count this one. I would leave this one open. All right, that one's open because I can't equal 1. I only want the line where it's less than 1. Now the other part, 4 minus x, might make more sense to you if you switched it around and said negative x plus 4. Most of us are thinking in that term. We start at 4, and we go down 1 and right 1 and down 1 and right 1 and down 1 and right 1. And so if you put a dot right here and then went down 1, right 1, down 1, right 1, down 1, right 1, down 1, right 1, and so on and so on and so on, I don't want to graph the whole line. I only want to graph the piece where it would be greater than or equal 1 according to the domain. And so really, I'm only going to start right here and draw that piece. Now, is that what Desmos looks like? Now notice the open circle up here at 1, 6 is going to get filled in by the closed circle, the purple circle here at 1, 3. So if you squashed this onto the entire domain, if you squash this onto the x and look at the entire domain, the open circle gets filled in by the purple circle. And so can anybody tell me the domain for this piecewise function? All real numbers. Squash it. Everything's going to get covered up. It's not continuous over the entire domain, though, because you'll have to pick up your pencil if you were tracing it. All right, now, in order to evaluate f of 6, you have to figure out if we're red or if we're blue. X equals 6. X equals 6, right? This says x equals 6. That's an x number. And so you have to figure out which piece we're looking at because we're not looking at both pieces. If you look at the graph, x equals 6, 1, 2, 3, 4, 5, 6. X equals 6 is over there. You don't need to make that mark on there. You just need to notice if we're red or we're blue. Is x equals 6 going to be red or blue? Blue, right? X equals 6 is looking at this piece and not the other one. The other one does not apply. Okay, if we're looking at 6, we're definitely looking at the blue part. And so all we really have to do is plug in 6. 4 minus 6 equals negative 2. F of 6 equals negative 2. So we look at negative 5. Negative 5, 1, 2, 3, 4, 5. Negative 5 is over here as an x number. Is that going to be red or blue? That's going to be red, all right? And think about it. What we're doing is we're saying, well, x is less than 1. Well, negative 5 is less than 1. So we look at that red piece, and the red piece says 2 times the x number plus 4. That's negative 10 plus 4 is negative 6. Got it. Graph the piecewise function. We did. All right. We can talk about continuity. We can say this is continuous over, and think about how you would trace it. You would trace from negative infinity to 1. So from negative infinity to 1, okay? And then from 1 to infinity. Now, the reason I didn't put a bracket there, I know that blue circle is filled in right there, but the reason I didn't put a bracket there is because we're not talking about the blue, we're talking about continuity. So when I trace this, oops, I have to jump up in the air and then land over here. Where did I jump? I jumped at 1. That's where it can't equal. Okay, that's where I lost my continuity. Okay. So example 3 is another piecewise. It's another piecewise. What I would recommend from the main title of the lesson, basic functions, you should know that one of them is a line and one of them is a parabola. Just looking at it, you should know that one of the pieces is a straight line and one of them is a parabola. Do you? Did you know that? Okay. So, I can do part A, evaluate f of 10, as long as I know which piece to look at. So notice either I'm talking about numbers that are less than or equal -2, or I'm talking about numbers that are greater than -2. So what color is 10? Is 10 red or blue? 10 is blue. It's definitely blue because 10 is greater than -2. And so if you're going to find f of 10, you're going to look at the blue piece of the piecewise function. And the blue piece says x squared, or 10 squared equals 100. -17. -17, is that red or is that blue? That's red, and that's red because -17 is less than or equal to -2. So we only look at the red function for that x number, for that part of the domain. -17. So we've got 2 times -17 plus 8. That's -34 plus 8 is what? -26? -26? Okay, cool. So graph the piecewise function. If you don't really need Desmos to do this, but I think Desmos is outstanding at showing you how this works. Okay, you know that -2, something weird is happening at -2. Okay, something weird is happening at x equals -2. That's where you switch from one to the other, from one piece to the other piece. So, if you were graphing the red piece, y equals 2x plus 8, 1, 2, 3, 4, 5, 6, 7, 8, up 2 and over 1, or down 2 and left 1, 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 down 2 and left 1. You've got a line that looks like that, except we only want the piece of it that's less than -2. So we don't really want the whole thing. Really, we're going to get rid of definitely everything or here. We only want the part of it that's going to be less than -2. Now, is that last red dot going to be an open circle or a filled in circle? You're looking right here. It's going to be filled in because that thing says equals right there. If this says equals, then we're going to have a filled in circle right here. I want everything that's less than -2, so I'm going to have this line right here. That's the piece of that function that is less than or equal to -2. Now the other one, x squared, we know x squared is a U shape. It's a parabola shape, but I only want the piece of that parabola that's greater than -2. All right, so x squared has a vertex at 0, 0. And if you've had me before, I always talk about the 1, 3, 5 pattern. If you start at the vertex, you go up 1, up 3, up 5, up 7, up 9. That's how I graph them because I'm lazy, I suppose. But if you go up 3, there's going to be a dot there. There's going to be a dot there. Okay. I don't really want that dot there, though. So I would leave that open. All I want is the part of the parabola that is greater than -2. That's my piecewise function. Okay, that's my piecewise function. And if you want to go to Desmos, go to Desmos. This one was 2x plus 8, I believe. And it was x is less than or equal -2. And so this point was the point, can't see, -2 comma 4. The end of that red line is at -2, 4. But it's filled in, right? It's filled in. So I'm going to knock that back down to like 10 or something. Okay. Then this one was x squared. X, I can do a shift 6 for my caret 2, x squared, but I wanted x is greater than -2. And this purple point right here is at, well, it's at the same place. It's at -2, 4 again. Only this time, it's got to be an open circle. I don't like how that one kind of disappeared. That's weird. But here, done. So the red circle, you know, the red circle is filling up, the purple circle is what's happening. But that's exactly what we've got graphed here. That's what we've got graphed. And so if you think about continuity for this one, if I start tracing in the left and I trace up on the red and then I switch over to the blue, did I ever have to pick up my pencil? I never had to pick up my pencil on this one. So if you had to talk about continuity, you would say continuous over all real numbers, because I never had a gap. I never had a hole to jump over. I never had a gap to jump over. I just went straight from red to blue, didn't pick up my pencil at all.